I think we're going to start now. Good afternoon, everyone. Thanks a lot for joining. Short after lunch break. We're going to talk about VXLAN Deployment Models, practical perspective. This session is normally presented by Victor Moreno. He is the body today. He's with us, but he has no voice. So I took over for him and going to entertain you guys for the next 2 hours. My name is Lucas Kradiger. I'm a technical marketing engineer working very closely with Victor. He will be in the question manager tool, so if there are any questions, please use it. We obviously also want to take questions on the mic if you feel this way. There's also another colleague from mine with me, Brian Farnham, also working with me on VXLAN. So all together, we should shake the room a little bit. It's a pretty big room. Thanks for joining, and let's get that started. Before you try to search for the PDF, I think there is a glitch in the system, so it's not uploaded to the system yet. We're trying to fix that. By end of the day, it should be there. We hope earlier, but it should go up to the system, and you find it in the app as well as on the web page. All right, with this, let me go through the agenda of the next 2 hours. We're going to talk about why VXLAN, just applicabilities, some fundamentals on VXLAN itself, overlay deployment considerations, underlay deployment considerations, and then we go into summary and conclusion and put the icing on the top by ending that so close to 3 o'clock. Why VXLAN, or actually where is the applicability there? I mean, the trend in the data centers goes into much more flexible fabrics. I want to do a lot of things there. I want to have host mobility everywhere, right? My virtual machines want to move, and my IP addresses should be everywhere where I want to have it, and I don't want to have choke points and similar things like there. Also, segmentation is a key. Multi-tenancy in the data center is a pretty predominant case, and people are adopting this. Obviously, also there's scale, which is addressed there. We were looking at that from an VNI space, and then also automation and programmability. And with the fabric itself, what we can build as it's L3 under there, so we have a lot of little nifty things which are going to talk when we go to the session itself. So let's start with the VXLAN fundamentals. And with this, by overlays. I mean, overlays gives me a separation from my underlying network with my overlaying network, and it allows me to build robust, high-capacity underlays with a lot of intelligent packet handling in there, and also programmability and manageability in there. And that piece is actually decoupled from what I do in the overlay space, where I build my virtual network, my superimposed network, if you want so. And that's where I do the segmentation, the mobility, and add the additional scale possibilities I have, and that's where I do the programmability piece as well. And this gives me a very well-integrated fabric approach by using L3 in the underlay, using an overlay, which gives me all that additional capability there, and we're going step by step through all of these possibilities we have across these overlay techniques. Let me look a little bit first at the overlay taxonomy itself. So we need to define a little bit what are these things, so you can follow me when I throw some fancy acronyms at you. And there are quite some which we could use. So let me start first with the underlay network. That's my base. That's where I start building everything on top of it. And then obviously I have an end host connected somehow to a physical network itself. So that's where the whole story starts. I built that. In the underlay itself, I have a control plane to get reachability for all my different networking components down there. My router, my switches, my forwarding happens there for that respective underlay. That underlay control plane talks obviously between what we call these edge devices. And it builds the reachability between these edge devices. And when we look at this slide here, the edge devices is actually the boundary from the physical network, which is attached, my server is attached, my virtual machines are attached, into where my underlay is and where I build my overlay from there on. So with this, you see the end hosts are actually not really connected from a reachability perspective in my underlay. I actually move it up into the overlay there, where I then build with an overlay control plane with these so-called VTAPs there, and the encapsulation my overlay. When I go through these things a little bit faster is because we're going and highlight all of these different points when we're going through this slide deck, when we're going through that session right now. So as said, we have VTAPs, virtual tunnel endpoints, or VXLAN tunnel endpoints, and specifically to VXLAN. And that's where we start the encapsulation to the other side. And in order to know where another VTAP is, we need to kind of have somehow a control plane which allows me to understand that piece. Some terms which I'm going to use, we have services, which are, for example, the virtual network instances, the VNIs. We have identifiers, VNITs, virtual network identifiers. We have NV, network virtualization edge, so that's where my VTAP, my tunnel endpoint, lives on. And then we have the VTAP itself, which is the VXLAN tunnel endpoint as an acronym or as a term itself. So we're going through all, and we're using all of these when we're going forward through the slides here. VXLAN had a way, or actually VXLAN started as a data plane encapsulation, or it is a data plane encapsulation. Basically takes a packet, puts a header around it, and sends it forward on on top of L3 network. That's where it started, and with this encapsulation and that data plane, we had data plane learning, or what we also know under the term flood and learn. So I send everything out to everyone, and then I learn if that respective person or that respective end host responds to me. That's where we start on with this. But there is actually a path which we're doing with VXLAN, and as you can see, the data plane encapsulation stays the same from the very beginning where we started on until where we are today. But up in the control plane side, where the learning happens, the reachability information about all the end hosts, there is a change happening, or there's actually a change there, and that's where we go from data plane learning, the flood and learn approach, which we also have today in classic Ethernet and all the other layer 2 semantics there. We're going into protocol learning, where we actually use an overlay control plane to add the end host information into. And at that stage, we're talking about things like EVPN, for example, which will also be part of this here. So let's look at the VXLAN packet structure. Just what we have in there, and how does it start? It starts with a classic Ethernet frame. So there must be something magic in there with these Ethernet frames that we have to always start with them. But obviously that's the predominant protocols we're using in the forwarding and the encapsulation term. So what we add there is a VXLAN header. And in the VXLAN header, there are a couple of different fields in there. And one of the most important fields is the VNI field. That's basically where my new VLAN comes into, my virtual network identifier. That's where I map my VLAN to when we're going through that. So that's I do and separate that. From that on, we have a UDP header on top of it. So it looks like that VXLAN uses UDP, I guess. And within this, within the UDP header, we have a destination port, which is obviously should be the same for every switch for sending the destination traffic there. But there is a very important piece of it in the source port we're using in VXLAN, and that's basically that we're changing that source port. Depending on how the header's being used, the tuple's being used in the original Ethernet frame, we take that and build a hash to change the source port to create entropy across an equal cost multipath network. So what does that mean? Normally, if I have tunnels, my source IP is the same, my source MAC is the same, my source port, maybe my destination port is all the same. So I will probably always use the same path when I look from my hashing across the network, because everything looks the same. Now with VXLAN, we introduced the entropy, and with VXLAN, we put the changing source port for the entropy. So we have a changing piece. So if I have multiple paths, and as my source port is ever changing on a per flow base, I use different paths to reach that destination. So this gives me a much efficient, much better way of sending traffic across the network. Top of that, an IP header, so we can use an IP routed network as a so-called underlay. And then obviously, where there's IP, if we're using Ethernet, there's also a MAC header there. And you see there, source destination IPs are the respective VTAPs. Source destination MAC changed basically on a hop-by-hop base in the outer header as we have a routed underlaying network there. And that's the VXLAN packet. So for some components in the network, which are not a VTAP, which are not terminating these packets, that's nothing else than IP UDP traffic for them. So if I don't speak VXLAN, I can still transport that packet across the network. I don't need to know anything about what's in there. Let's look a little bit more at how we're doing the learning in these areas. So we look at the data plane learning there, and I'm going to explain how it's being done in multicast first. And when we're looking there, we're having two hosts, a web virtual machine, a DB virtual machine, and obviously these guys want to talk to each other over a layer 3 core, and on top of it, that VXLAN network, which allows me to build multiple services there. So my VTAPs are joining a multicast group. And I need that multicast group because things like ARP messages or other broadcasts are actually multicast when you look at them a little bit closer. So we need to make sure that we can send these multi-destination packets also to multi-destination endpoints in a certain way, and that's what we are actually using in the data plane learning there. Not only just to send this packet around, it's actually there to learn my neighbor virtual or physical machine I want to talk to. Basically the same thing we're doing in Ethernet, just now one layer higher, right? So the VXLAN is kind of representing my layer 2 segment up there. So obviously can do that with another segment as well. So we have purple and we have green, and then can separate these destination groups, these multicast trees, for a given VNI. So only for hosts which are in the same segment, which need to communicate to each other, I can use the same multicast group, and amongst that VTAPs which are serving these multicast group, these VNIs, we will have that multi-destination traffic happening there. So packet comes in, where do I want to go? I encapsulate it in a multicast message, sending to all the destination members which are belonging to the same segment I'm serving there. So that's the data plane learning. So when we look at this a little bit closer, VM1 sends an ARP request on VTAP1. We're encapsulating it and send it to the group, which is mentioned up here. And I think there is a laser pointer maybe in this one here. We're sending to the group up here, and the group represents a multicast address. We're sending it into that and replicate it in the network itself. And from there, we send it to the respective other destination VTAPs, which are serving also other VMs in the same stretched segment in there. And from this, we learn. From this, we know now VM1 is behind VTAP1, because that VM1 sent that respective ARP request. And with the group we used and with the VNI we used in the encapsulation of that message, we know it's belonging to a certain segment. So when we look at the response which is happening after that, a response to ARP, which is a broadcast, is a unicast. So we're actually sending that ARP response back, encapsulate it, and now we know I want an answer to VM1. That's where the ARP response needs to go. So I send it to VTAP1, encapsulate it, send it unicast across the network to VTAP1, we decapsulate, send it forward to the VM, and with this we learn again. So that's what we call data plane learning or flood and learn. Now, in overlay networks, or in VXLAN specifically, we have multiple ways how to build overlay networks. The start is, on the very left-hand side, the network overlay. That's where we have the VTAPs being configured in the hardware switches. There's obviously another way of doing it, where we put the VTAP into the software, in the virtual switches, in a hypervisor, for example. So while network overlays can cover basically everything, the software or the host overlays are mainly focusing on the virtual environments there. And the golden thing to put both environments together, that we can have virtual VTAPs and physical VTAPs, meaning the network side overlay is obviously the hybrid, where we can mix and match the twos together. Now let's talk a little bit about the evolution in VXLAN. There are multiple things we are doing, and I explained before how we do flood and learn with multicast. We're also looking at how we can do multicast independence. Not everyone is very well experienced on the multicast side. So there we use something which is called head-end replication or ingress replication. And we allow a control plane on top of it to dynamically discover the VTAPs. So I don't have to search first for a VTAP. I actually know him proactively and send only the information to the VTAPs which are actually interested for a given segment, for a given VNI. Other revolutionary pieces are protocol learning to prevent flooding. If I have to go all the time over that flood and learn semantics, I obviously load something in my network. If I can proactively learn and populate the information without sending the flood across the network, across the VXLAN, that's another way of doing it. That's where we bring the protocol piece in there. So we're having a control plane which knows about IPs, MACs, and distribute that across all the members in a given network. And as we are not only having MAC and IP, we also know the VTAP where it is behind. We can proactively forward towards that VTAP to reach the destination which you want to have. That's what we're doing in protocol learning, and I show a couple of examples during this here. External connectivity is another piece. VXLAN hardware gateways to do encapsulation for stretching things. It's also the integration of hybrids, or how I attach a host redundantly. That's part of the external connectivity there. And then the last piece in the evolutionary part is IP services. VXLAN routing, the integrated route and bridge approach we're doing in there, and how we can distribute the gateway to avoid choke points and make a more efficient forwarding decision right as close as possible to the end host. Let's look at the control plane first, what we can do there. And this is for VTAP discovery. Proactively knowing about all the VTAPs which are in my network itself, which are joining me for some overlay services. And what I do is everyone sends his own VTAP information, in this case here, to a route reflector. They're actually doing this in the Nexus 1000V for quite some time in between. So he's sending that to the route reflector, and as the term route reflector says, he sends it to all the other guys which are peering with him. And with this, I actually can build a topology information and know exactly which of the other VTAPs can do that other ominous head-end or ingress replication, which we're going to look at it right in a second. So now I know everyone. Well, I probably don't know everyone in the room, but at least in my network here, I know most of the guys. Now with this, as I know that somebody is respectively the person who is serving a given VNI, I can now start thinking about where to replicate to without the multicast piece. So let's look at this. When I have a BUM frame we can use the ARP request from before, or BUM is just broadcast unknown unicast or multicast traffic. I want to send that to respectively pod 2 or pod 3. So what I do is I encapsulate it. I want to encapsulate it, but I need to encapsulate it with a destination which is multiple sites, multiple endpoints, because I have no clue where that given destination system is. So with ingress replication, I multiply that packet at the source. So wherever the source host is connected to, that first VTAP copies that packet and sends it unicast-wise across the network to all the neighbors which are serving that respective VNI itself. So I don't need any multicast anymore. So I can use unicast and ingress replication to do so, but I need to know about all the potential neighbors I have and send it to them respectively. The next piece goes into protocol learning. So more proactively learning about the end systems which are in a given network. So a given VTAP advertises a host route. And with the host route also the MAC address of the end system to the given route reflector. So a given route reflector, as it says, reflects it and sends it, and sends it to all the other guys, to all my other VTAPs, my buddies. And from there on, I know exactly which endpoint is behind which VTAP. Do I need to go and flood for him to search him? No, I don't have to, because I now have a control plane which is proactively serving me the information to reach the destination there. Everyone okay? No? All good? I saw 1 thumbs up. Everyone good? 2 thumbs up, 3 thumbs up. Okay, let's continue. Now the VXLAN control plane in the overlay we're actually using there is multi-protocol BGP based. And in multi-protocol BGP we have the extension of using an LLRI of EVPN, which gives me not only the IP addresses in that control plane, it also gives me the MAC addresses in there. And many other information, obviously, as well as what you have heard, which is my VTAP, which is actually the host being behind, and some of the segmentation IDs. So when we look at a network which is using that control plane in the overlay, we obviously have our leaf switches, which you see with L1 to L4, and all of these switches are building an adjacency with a route reflector for easily serve that and reflect these information as you have seen previously. So now I know about everything in a very easy way and in a very standard way. With this, I completely decouple any host information from the underlay at all, because it only acts in the overlay itself. So how is my underlay convergence now when I don't have any host objects in there? It's getting pretty lean, right? So I have my VTAPs, my point-to-point routes, that's it. In the overlay, I have the end hosts. So let me go a little bit about host advertisements in EVPN or in the VXLAN control plane here specifically. A host gets attached, and with the host attachment, I actually start learning that this host exists there. And there are multiple ways how this happens. We know when a new host comes online, we actually ARP for my default gateway. Oops, it's first packet, right? I already know that host exists there. But there's also other ways how we can discover the host just based on any packet which is actually sent out from that given system. Even a MAC learn is actually enough to populate the control plane. So this goes to the route reflector. We give a couple of information in there. So as said, we're having MAC as well as an IP information in there. We have obviously the VTAP in there, and it's not only the IP address of the VTAP, we also have the MAC address of the destination VTAP in there. This is pretty important information for that. We get the VNI, which is my segment information, to not call it VLAN over VXLAN. And then there are a couple of additional community pieces which tell me what encapsulation they're actually using. Is it VXLAN in our case of the discussion here? And then you also see on the bottom a sequence number of 0. just for this here. Now, when we look at the control plane itself, you see up there MAC 1, IP 1, we see VNI 5000, IP L1, MAC L1, VXLAN, and 0. So we know exactly where it is and what it's capable of doing and in which segment that respective host is being in there. So that's my host 1 in VLAN 10. And now the fancy stuff starts. Because I guess everyone wants to do some vMotion thing. So we're going to move that host. We move it to a new VTAP, to a new edge device. So what happens? We signalize again. And now we signalize from a new VTAP, so we increase the sequence number. So with this, we know now that host is behind the new VTAP. So what we're actually doing is we're starting withdrawing the old message and updating it with the new information of where the new VTAP is in there. And we can go on and forward traffic now. As we overwrite the route, which was previously on leaf 1, with the more updated sequence number of the same route from VTAP 3 or from L3. And that's what we're doing in the control plane by learning where the end host is being connected to. In VXLAN, there are different gateway modes. So we have layer 2 gateways, we have layer 3 gateways. Layer 2 gateways, obviously, VLAN goes into a VNI. I take a VLAN, .1Q encapsulated, get into a switch, map it to VXLAN, meaning map it to a VNI. And that's where we just get a much, much larger number than after that, as you can see in the top orange piece. In the bottom one, we have L3 service. So we can do VXLAN routing. Either we do VLAN to VXLAN routing or VXLAN to VXLAN routing when we have a node which is acting as a gateway and we want to change into another VNI there. So these are the services we are supporting, and in the bottom you see a little bit of information which platforms are actually supporting VXLAN bridging versus VXLAN routing in these different modes. And you see it's pretty broad what we are having there from a portfolio perspective itself. So that's basically VXLAN as a fundamental. And is everyone okay so far? Any particular questions you want to raise in the room? Do you mind to go to the mic, please? If I can hear. You're good? No questions? Yeah, nobody wants to go to the mic. Brian, Victor, anything we should clarify? Please.
Does your updates go to both route reflectors when the host moves from one VNI to another?
Okay. When my host moves, is the update going to both route reflector? The update is going to all the route reflector which are peering with me. It behaves exactly like BGP would behave. So we're using all the technology we already have for decades in multi-protocol BGP. As we know, over the time, multi-protocol BGP or BGP per se evolved and converged much faster. So the scan time is not anymore of a concern. I mean, waiting 60 seconds until we get the host move actually being recognized, I don't think that happens today. That's gone. All right. So let me go into the overlay deployment consideration. There's quite a section which we're going through. And to start up here, there are two different overlay services which I can provide in a given network. You had a question?
Yeah, sorry. Took me some time to get the mic.
No problem. Welcome. Is it on? Should be on.
Test. There we go. So quick question back on the virtual machine move where we changed the sequence number so that we could withdraw the route on the first VTAP. So when that virtual machine moved, are we relying on that virtual machine to send some type of an ARP query, or how does that VTAP know that that virtual machine's arrived on that switch?
It's a very good question. So thanks a lot for asking that. I was waiting. There are no questions coming. So in a virtual move scenario, and let me just keep that slide up here. In all the virtual infrastructures, when a virtual machine moves to a destination, the destination virtual switch is sending out a couple of messages to acknowledge that move, basically. It is reverse ARP, GARP, or some other messages which could be, but it's ARP-based mostly. Not only this, as we are in-band learning in the data plane, if that host is continuously speaking, we also update from that perspective there. But it's obviously, yes, ARP is one of the messages we are using for this.
Thank you.
Thank you. Yes, please.
Would you recommend a host connected to multiple VTAPs?
Can I have a host being connected to multiple VTAPs? Yes, I can. I have a dual homing approach in VXLAN to connect a classic Ethernet host, and it's actually what we're using VPC. And I'm having a couple of slides on this one. We obviously always want to have dual attached hosts and stuff like that in the network itself. So just to make sure the question got clear, dual attachment of end hosts to a VXLAN VTAP or multiple VXLAN VTAPs. All right, so let me start here on this one. Oh, another question? Do we have something like a TCN in VXLAN to do bulk updates? We have, yes, so we have bulk updates in BGP, which is already in there from the general protocol itself. So if it would be multiple moves happening at the same time, we could package them and send them as a bulk. Would it be possible? Yes. Please. Say it again, sorry, please. Okay, that's a good question. That's a good question. So with EVPN, do I still need multicast? That's a very good question. I normally have a slide with Zeus and saying it's the big myth there. So BUM traffic handling in VXLAN is a data plane operation. It's either handled by multicast or by ingress replication. EVPN as a control plane can allow me to learn dynamically my ingress replication neighbors, but it does not remove the requirement from any data plane replication for BUM traffic. One additional point I want to make, as we are trying to learn as much and as close as possible to the end host, the potential BUM traffic is already reduced with EVPN. But there could always be a BUM packet apart from just the learning, which I need to forward, so ingress replication or multicast would still be a valid case you should consider in the underlay. So far answered? Thanks. Okay, so let me go forward, because some of the questions you're actually raising I tried to answer in the upcoming slides. Just something in regards to the host update, or?
Yes. When you move the VM from one data center to another, how are you guys addressing the routing concerns when the VM is in data center number 2?
Okay. How are we addressing the routing concerns when we're moving a virtual machine? You're talking about the routing outside of the data centers into the data centers? Yes. Bear with me, I have great slides on this one.
So is the underlay BGP, is that expected to work just like ISIS, that you're not supposed to go in and configure it, or are we supposed to be able to configure BGP and do an underlay?
Very good question. So do we have to configure the underlay is the base question, and do I have to configure the overlay control plane? As said, we are relying on a layer 3 routed network. So it's your power to use all your CCIE routing and switching skills to build that network there. Then the overlay control plane is obviously also a manual process just to configure it. But I always do a but. We have a lot of automation features which we can use in order to leverage and do that process in a more streamlined and automated way. But it is NXOS, CLI configs, routing, switching, what we're actually doing there. All right, I think I have to proceed here, otherwise we are running over, I guess. Type of overlay services. We have two different types of services which we can provide in VXLAN there, and there's obviously the layer 2 service, which is, I would call it equivalent to building a layer 2 network on top of a layer 3 network. And then the other thing is really building a routed network on top of a routed network. And when I think of this piece over there, obviously there's multi-tenancy coming in my sense right away. And do I have to have only L2 or only L3? No, obviously not. I can merge that together and can do integrated L2 and L3 at the same time. So let's look at the L2 first. So we have obviously layer 2 gateways, and you see the layer 2 gateways can be either on a network device, which you're seeing there represented by a switch symbol, or it could be on a virtual switch close to the virtual machines we're seeing on the bottom there. We also see VPC in that case, and we're going to talk about that piece there to achieve the redundancy, which I already said. So we're building a layer 2 service. We are actually building a layer 2 segment on top of a layer 3 network, and you see that represented in orange and green, and we're going to terminate that on the VTAPs and just have that tunnel being happening between these VTAPs and creating that. And actually the green and the orange is what we call a VNI, and there are obviously 2 VNIs in that specific case attached to the different VXLAN L2 gateways. How do I configure it? I configure a VTAP, the NVE interface, obviously. I have a source interface where my whole VXLAN traffic is coming from, and we use a loopback there. It's probably good to have a loopback because that thing will never go down, right? As long as I have reachability, there will not be a change. That sort made a lot of noise. All right, so the other thing we need to add is what do we actually want to extend? And there you see the member VNI of 6000, which is my layer 2 segment I'm actually creating there. That could be the orange or the green, which I showed before. And behind that, you see the multicast group, which is taking care of my bump traffic on my multi-destination traffic in this specific configuration here. What else? Well, obviously, most people have VLANs today, and just having a VNI and a VTAP in a switch will not help me to extend the traffic at all. So I need to get that VLAN on the classic Ethernet side into the switch and map it to a respective segment, to a respective VNI in that case. And you see that on the left-hand side in a very straightforward way with the VLAN 3002 and the VN segment of 6000 underneath. The VTAP configuration you saw before already is on the bottom for the interface NV1. Now, we have 2 different ways of configuring this in our switches, and it depends a little bit on the different functions we have. You see on the left-hand side the classic mode, or what we call empty light or multi-tenancy light, versus on the right-hand side, which is empty full or multi-tenancy full with the EFP or VSI CLI model. And in this EFP or VSI CLI model, we actually don't have VLANs anymore. So whatever is incoming to the switch, we look at the .1 queue, we map that to a bridge domain, and then attach that bridge domain to a member VNI, and that's how we do then the encapsulation forward into the VXLAN. So 2 different models there. To look a little bit more detail into the VSI CLI model, as the left-hand side with the VLAN to segment ID is pretty straightforward. The right-hand side is using something which we call an encapsulation profile to listen to the .1 queue messages or the .1 queue tag traffic on the Ethernet and encapsulate it respectively. Please, sir.
So the BD model, the bridge domain model?
Yes.
Does that employ the same as ACI where you're taking the layer 3 subnets and separating them so you can actually put more address space within a bridge domain?
Okay. It's a very interesting question. So is the bridge domain model we are doing here in the switch the same as what we're doing in ACI? So generally, I can today put multiple IP networks in a single bridge domain, which is nothing else than a VLAN with an SVI and multiple IP addresses and secondaries in there. Yeah, you can always do that. Think of it, the bridge domain is nothing else than a VLAN with an unbound numbering. The VLAN is bound to the .1 queue encapsulation. The bridge domain is the same resource, but not bound to any encapsulation. It gives me more room. So I don't have to create bridge domain 10 if I want to receive traffic from VLAN 10. It's just an ID in the switch to address my resource. It's just a number. The meaning of the bridge domain identifier is switch system local. Like a bucket. Yes, it's like a bucket. All right, so I stopped at the bridge domains where we basically actually mapping everything together and have that encapsulation profile which we attach to the interface, listening to the .1Q traffic in there, map it into the bridge domain. When we are egressing, we attach it to the VNI and do the VXLAN encapsulation respectively. Now, obviously, there's also a component in the L3 space, right? I mean, in VLAN, we used SVI. That's where my IP address was being configured on. In the bridge domain, I obviously don't have an SVI anymore because I don't have a VLAN. What I have there is the so-called BDI. And you see in the middle of this slide here, a section on the right-hand side where we actually have interface. Sorry, that's layer 2. Sorry about that. That's actually how we attach the service instance to the interface. Sorry about that. But actually, it's a good segue to go forward. So let me clarify that very shortly. Physical interface, trunk or access, VLAN, other site, VSI, encapsulation profile, physical interface, map it into bridge domain. I actually said that, I was just confused on the slide very shortly. Sorry about that. But let me go into the routing approach. Yes, please, sir.
What happens when you connect a switch to a VTEP and when you create a loop?
What are you doing? What happens when you connect a switch to a VTEP and you create a loop? It loops. Yes, okay, so let me open it a little bit up. I'm building a tunnel between two VTEPs. So I have two switches, which I have a VTEP on top, and I do a VXLAN tunnel on top there. And I put an Ethernet cable underneath. So I'm a cleaning lady in the data center. I hope nobody has cleaning ladies in the data center which are plugging in cables there. So spanning tree is not running over VXLAN. So obviously it's stopped down there. So we're not forwarding BPDU. So you would have both paths being active, results in the loop. What you should do in that regards is protecting your border. And actually, we're not only saying protect your border by configuring spanning tree, actually use features like storm control, BPDU guards, and things like similar approaches. So far answered? I don't want to go into what we have kind of protection in the EVP and control plane, because there we have protections in order to prevent loops for being infinite. Okay. So let's go back to the L3 piece here, where we see my gateways down on the bottom. My layer 2 gateways redundantly connected there with VPC and so on and so forth. But I need somehow routing between these segments. I mean, I needed routing between VLAN 1 and VLAN 2 before, or actually just the networks which are in these respective VLANs. So now I need to have the same thing in the VXLAN space. And you see there, I create SVI. I reach that SVI over a VXLAN VNI, and then I route into the other side. And that could be that centralized routing approach we're seeing in here. And that's what I actually wanted to show before. So that's the configuration of what we had before as an SVI. Let me show it here down. Interface, VLAN, IP address, HSRP, very straightforward. It's the same way how I would do it when I would do VLAN itself. Now in the bridge domain case, we do it a little bit differently, as we don't have a VLAN anymore. We're actually going into the interface BDI, which is nothing else than a virtual bridge domain interface, which is respectively bringing the L3 hop into the game there. HSRP goes exactly the same way underneath there. Yes, please. Give me 1 second on that question. So the question was in regards on what I'm doing with HSRP exactly there. When I just have two SVIs or two BDIs, I do HSRP in a very traditional way, active standby. But obviously, you can create a VPC domain on these gateways. When you build a VPC domain, we can go in HSRP active-active, so the data plane forwarding would be active-active there. And we also can use a feature which is ARP synchronization in order to make sure that these tables are being synced in between there. also, with VPC being used on the L3 side, I obviously can also use VPC in the L2 gateway side to redundantly connect the end host, which you actually asked before, a couple of minutes before, right? So we have VPC for end host, we have VPC for the gateway approach as well. How does that look like different than what we do today with VLANs? No more spanning tree, right? We have a robust L3 underlay. We have all path forwarding. We don't have to care on any loops in the underlay itself. We build an overlay on top, protect our border, obviously, to make sure that we don't impose loops into the overlay itself. But we have kind of the same approaches in how to configure it. It's no complete new magic. Yes, please.
So from the VTAP to VXLAN gateway, can there be a port channel northbound?
Yes, from the VTAP to the VXLAN gateway, can I have a port channel? So respectively, either a virtual port channel here or a port channel down here to a host can obviously be there. Yes, and up north, between the L2 gateway and up to the L3 gateway, I can do a port channel. But I obviously would not do a VPC port channel down to the switches there because I don't need that. I'm using a routed approach in there. All right. So with VPC in the game now, we have to have a couple of considerations in there how actually VPC now works in VXLAN. We're using an approach of the two switches share a personality in regards from a VTAP perspective. We use something which we call the Anycast VTAP, as you can see up here. So what we're basically doing is, you two guys are buddies. You two guys have a own personality, but you need to do something together. So you guys share one thing, and that's that Anycast VTAP address, which is the same IP address on both of the nodes. So whenever I try to address traffic in direction of a host which sits behind a VPC complex, my destination VTAP IP address is actually that Anycast VTAP address, which allows me to go either to the left guy or to the right guy, meaning one of the two members in my VPC complex, as you can actually see down here. It's a little magic, but in routing, we're doing actually that Anycast VTAP approach or that Anycast approach for a long time to, for example, rendezvous points or similar kind of infrastructures. So hardware redundancy for VTAPs. We talked about VPC a little bit. We see on the left-hand side actually exactly that denotation in detail. We have two switches, two layer 2 gateways in that case. IP-A1 and IP-A2 are the individual IP addresses of these two switches for the VTAP. And on top of it, we use a shared Anycast IP address, which is exactly the same. So no flapping between left and right. We're just forwarding based on the flows and based on the destination IP there. Now, I can also put the VPC approach there to connect my external existing first hop routing. So you see down there on the right-hand side, I'm having routers externally connected there, which actually representing my SVI I'm using to do inter-VLAN or inter-VXLAN routing in that case. So I come to the Anycast VTAP, and wherever I want to go, is it left or is it right, I can route from there and route beyond the network itself, meaning beyond the VXLAN overlay network itself, which is in my data center, to the outside world, to the WAN or to the DCI place. I actually don't have to route at all in that case. I actually can just connect a layer 2 DCI service, for example, OTV or VPLS, on these given router symbols there and extend it from a layer 2 perspective further. Now we're talking L3. When I'm having layer 3 services in my VXLAN itself, and I do routing to the external world for WAN or for DCI, I have a very efficient way of doing that, right? It's nothing else than a router point which I need to reach, and then I route beyond, do point-to-point full mesh links as represented on the left-hand side. I don't need anything like HSRP in that case, because I do the routing somewhere else. I do it inside my network before I even go there, because my fabric, my overlay, is a layer 3 overlay, right? So my gateway is somewhere else. My gateway is in the fabric. I reach it routed to the border. If I don't have that, if I have an L2 VXLAN overlay like on the right-hand side of the slide, I actually need to have somewhere my gateway, and that's exactly where my VPC domain with HSRP comes into the game. Where I use there on top of that my gateways actually, and then I just transport beyond routing over the port channel to reach my next hop or reach an external network in there. These are kinds of things we're already doing in classic Ethernet today, so it's also applicable for VXLAN. But it's pretty important to see the different services we can use in VXLAN, where we have the L3 VXLAN overlay, which is all routed in there towards exit. So my gateway is somewhere else, and we're going to talk about the gateway itself, where the first hop is. And the other thing where we have an L2, where we need to reach that point, that border leaf, which does the HSRP for me, and then routes beyond to the outside world with that VPC approach in there. And that's the segue from centralized gateway to distributed gateway. When we talk about that centralized gateway, it's basically what I explained, these two top switches, the L3 boundary on top there. Whenever I want to go there, I have to cross first the layer 2 VXLAN service. There's my L3 boundary, and from there on I can route. What we're actually doing these days, we're moving the L3 boundary closer to the Tor, or actually on top of the Tor, as close as possible to the end host. So with this, I have my L2 and the L3 boundary right where the classic Ethernet stops and the VXLAN starts. So my fabric could be hybrid, meaning L2 and L3 there, depending on where I want to go. We call that the distributed anycast gateway, and I have a couple of slides in there. And the main point, what we're actually doing is where's the choke point now for my L2, L3? It's distributed. It's not anymore at one centralized point. It's basically everywhere where my hosts are connected to. So for the distributed IP anycast gateway, to explain that a little bit better, we took this representation here. So all of my top of rack switches are becoming L3 gateways from a VXLAN service perspective. Everyone is actually hosting not only the same MAC address, also the same IP address for a given VLAN. So when I do host mobility from one switch to the other switch, what does change for the end host? Nothing. As long as it's same VLAN, same IP, same MAC address. So it's much more seamless when I do the overall movement and the overall forwarding. So you also see the representation of VPC there. We obviously also support VPC in distributed anycast gateway by using the port channel hashing over the left and the right port and forward then respectively from a first hop routing to the remote sides. So distributed IP anycast gateway. Is it HSRP? Are we doing any state exchange there? No, we don't. And I'm going to show you how that forwarding semantics works in that specific case of distributed IP anycast gateway in a couple of slides from now. So that's my network down there. We see there the layer 3 fabric. You see 3 red markings for my layer 3 gateways, and we go and dive into 2 of them to show how the communication works in that respective IP anycast gateway view. So what I obviously have in that switch, in that VTAP, I obviously have the layer 2 segments created. It's what I want to have, like the layer 2 service over VXLAN. But also I have SVIs, which is my first hop routing destination, which I want to go whenever I want to go in a different subnet. So you see the orange and the green, which I initially showed before. That's that L2 gateway stretch, which started in the L2 space before. And now we're going to add the L3 gateway piece, which is actually doing the VLAN to VXLAN routing, represented with that VNI X in blue. So whenever we route, we go into VNI X in the blue piece. Whenever we bridge, we stay in orange or green, depending on which VLAN I am. So let me open up here the second VTAP, and now that looks very abstract, right? But actually it's a very nice representation which Victor did here to explain these two semantics of routing and bridging, or L2 gateway and L3 gateways in VXLAN. So this represents two VTAPs. And between these two VTAPs, we obviously extend layer 2 traffic. That's orange and green. So that goes across our underlay, our routed network. As you also can see is we have VLAN A in green on the right-hand side and VLAN B in orange on the right-hand side. On the left-hand side, we have VLAN A prime and VLAN B prime, and I'm going to explain why this could be, for example, a completely different VLAN in a second from now. For the extension on the layer 2 side, we have VNIs, VNI A, VNI B. And then up north, we have VNI X, which is taking care of the routing whenever we want to go from left to right. Good so far? We have more slides on that, so death by PowerPoint could happen today. So interface VLAN, this is the classic mode, or the more VLAN-based mode, which I'm going to show. It's much more easy right now to follow this, as there are a couple of new concepts and semantics coming in, so you're more familiar probably with this. So interface VLAN, straightforward. It's good advice to do no shutdown on them. Otherwise, it's probably not running. You put it in a VRF. So when you start doing L3 service in the overlay, all these interfaces, all that traffic will actually happen in an L3 instance, meaning in a VRF there. IP address, you see there 10.10.10.1, and every switch which is serving VLAN 10 will actually have exactly this IP address being configured. We don't have any more individual IPs for the gateways and then a VIP, a VIP address sharing with HSRP. They all have the same IP address there. And then actually the magic command which makes Anycast gateway working is that fabric forwarding mode of Anycast gateway, which you set on a given SVI and make it actually behaving this way. Underneath, you're seeing the VRF context, which you can configure on the switch. Obviously, as we're using VRF on the interface up there, we also want to have that there. And you see the VNIX. And the VNIX is actually the routing VNI. So whenever we go post-routing, we use that VNIX in order to do so. Now, as we're using a control plane, which is MPBGP based, and multi-protocol BGP uses something like route distinguisher and route targets, we obviously need to configure them under the VRF, otherwise we will not be able to forward with these respective information. That looks a little bit different now, right, than just creating a VLAN and an SVI there, but it's pretty straightforward, I would guess. Now, when we go in the VXLAN control plane, which we obviously need for routing, we need to somehow exchange these routing information. We're using obviously a VPN-based approach. You saw the route distinguisher and the route targets. We don't want to have like VRF flight hundreds of peerings from one switch to the other switch and in a full mesh manner. We do one peering, we do it VPN-based, and for this we're using this address summary of L2 VPN, EVPN. That's where we transport all the overlay information in there. And as you can see, whenever we need to break it out on a given switch, meaning a switch is serving that VRF, it's basically like an MPLS-PE configuration. You configure the VRF and get the respective VRF being created there and the routing information being advertised in. Let's have a closer look on the bridging side. I promised I'm going to explain why VLAN A and VLAN A prime could be a completely different number, because the VLAN becomes only local significant. When I look in VXLAN, I'm not using VLANs anymore, right? I'm using VNIDs. I use a different way, an abstracted way of a VLAN, of a segment, the layer 2 segment in that case. So I could theoretically have VLAN A mapped into VNI A, mapped into VLAN A prime, or in numbers, VLAN 10 to VNI 30,000 to VLAN 50. Because the VLAN is only local on the switch or on a pair of switches when we're working with VPC. Don't have to, but you could. So VLAN is now completely something different, right? It's just a number again. I have to check on the virtual switch, but it's a number. Now, let me explain a little bit how traffic forwarding works from the very, very beginning in a network with distributed IP Anycast gateway and the VXLAN EVPN control plane. So the first thing, obviously, is host PM1 needs to be known to the control plane itself. So it becomes available, sends out an ARP request because he wants to register with the gateway. We receive this information, and we distribute this information right away in the control plane. So with this, my VTAP on the very left-hand side already knows about physical machine 1 or PM1. It knows its MAC, knows its IP, the segment he is sitting in, and the VTAP IP address. So basically the location where he's sitting at. And we obviously get a response on that ARP request in order to answer for VM1. So let me go to the next slide. So now we know about PM1. PM1 is known to the control plane. Now VM1 wants to talk to PM1, and we're in the same subnet, right? It's a bridging approach we're doing here. So he sends out an ARP request for PM1. So we do that, send it to the switch. With this, we know already where VM1 is now, so we distribute this information. And we actually don't have to wait for a response from PM1. We can locally answer that ARP request with an ARP response with all the information relevant for PM1. So with this, VM1 knows completely up at PM1. Same subnet. And with this, we could actually start forwarding. Now, in case there would be a miss in the routing table, so meaning PM1 would not be known, we would actually just forward that ARP request across the network, and then on the response, we would have learned it. So ARP is actually a pretty nice thing to get a lot of learning going in there. And once I have learned, I have the control plane which assists me. Now, obviously, subsequent ARP requests could again get flooded, but we don't want that actually. And with this, we can bring something in which is ARP suppression. So subsequent ARP requests from an end host will always be answered locally if I know about that device which is somewhere remote. So how much bump traffic do I generate then from a broadcast, from an ARP broadcast perspective? It's close to 0. It would only be for any routed, for any silent hosts in that case. So before I go into the IP forwarding, are there any specific questions on the learning and ARP suppression which we just went through? Or maybe the gateway even one step behind? We're all good? I know it's after lunch, so I'm getting tired as well. Yes, please.
So a couple of slides before this, so in order for the two different nodes with the same anycast IP address to recognize each other as a different location of a switch, you use basically a BGP peer address. Is it correct statement?
Give me a second how we do the distributed IP anycast gateway from a distribution and information perspective. I will answer that. I have a couple of slides on this. I will explain how it in detail works. Yes, thank you.
Might be along the same question I get from the host that's
You can get closer to me. I have a mic. My name is not Mike, but I have a mic.
It's Mike now. So the question is about, I get if the source moves or wherever it's coming from, but on the other side, if it's in the network, right? It is possible if you're using Anycast across whatever the environment is, whether it's another data center or just another room, that you could actually be talking to that gateway before you actually hit a VTEP to come back to the other destination.
Okay, so let me try to answer that. Hopefully I got it completely, so let me see. So if I have multiple data centers and I have my network stretched across multiple data centers, well, let's take one subnet is stretched. So I can move from one data center to the other one. Theoretically possible, right? So there is a move situation which happens. In order to get that properly working, I have to extend the control plane between the two data centers. So I need to extend the reachability information in my EVPN control plane from one data center to the other data center. I don't need to feed it into the WAN, but I need to have that consistent control plane information across both data centers. Is that answered? Does that fit your question?
It fits. I'm just looking at let's say the client that's talking to it. I get how all of the peers don't talk to it. The server will talk to its local gateway because all of those servers are going to have a gateway. I get that. What I'm a little unclear on is inside of the routing for like the client, I can hit using any CAS, right? When you're using any CAS VTEP, I can actually hit the wrong data center's gateway before I actually
Okay.
get over to another.
Okay. Okay. So the question is more, how do I enter into the data center? So I have a subnet which is stretched. Both data center announce the prefix of that given subnet, but my host might have moved and my entry point is on the wrong subnet from a routing perspective. Bear with me. I have a couple of Lisp slides to just answer that in front of. But it's a very good question. Ingress route optimization is a piece we're handling, and we're working on this one, and we actually have it already available there. So let me go into this, and I will go and answer your question as well in the flow of the slides. It's in there. So same as your question will be more detailed handled there. Okay, so now I want to talk between VM1 and PM1 in a bridged environment. So I create my frame, actually, my packet from VM1 to PM1. So source MAC, destination MAC of the individual systems, source IP, destination IP of the individual systems, and if it's transported across a trunk, I obviously also have a .1Q tag or maybe an access port in that respect. So I go on top of my first switch and do a lookup, where is actually my PM1 MAC, and the response is it's behind destination Tor on the very right-hand side, and the VLAN of 123 is actually mapped to 10,000. So that's all the information I get on that first top-of-rack switch. And with this, I'm actually creating an encapsulated packet, or start doing the encapsulation in there. So I'm adding the IP header. And the IP header, obviously, is the source Tor VTEP IP to the destination Tor VTEP IP. So that's in between where I built the tunnel. The VLAN becomes the VNI in the VXLAN header. The MAC layer inside of the encap stays the same. PMMAC, VMMAC, and the IP stays the same because it's a bridging situation here. So we don't change anything in the original classic Ethernet frame. We send it across the fabric, and once we reach the destination Tor, we do a local lookup. Where is actually that destination MAC, behind which port, in which VLAN? So with the decapsulation, we send it down on the classic Ethernet in the respective VLAN. And now, as the VLAN could be completely independent on each side, because the VNI bridges it together, here we go, local VLANs, global VNIs. Let's look at the routing approach. The bridging was pretty simple, right? VLAN, VNI, VLAN, done. Source MAC, destination MAC, same, nothing changed. Routing is a little bit different, but it actually works exactly how routing does. So in this case, we have that common VNI X, and the VNI X will always be used post-routing. When I need to go from one VTEP, from one switch to another switch, and I have a routing operation, because my destination is another subnet, I will use that VNIX for the encapsulation process. So go from H1 to H4, which is a routing operation. I come from orange and I want to go to green. So I go into orange, do a routing lookup, where is actually my host 4. Host 4 is in a remote VTEP, and it's in that virtual routing space of that, where that SVI, where the network is in there, or simply said, in that VRF of blue, or which is using VNIX. So encapsulate it, send it over there to the remote switch, VTEP2, do a local lookup, and send it down the wire. So one question. I don't have anything here, but you give me your email address and I will send you something. Post-routing. Post-routing. Do I care what my source VLAN was? Do I care? Who is first at the mic? No, okay. No. The answer is no, right? The answer is no. Post-routing, the VLAN where I come from is completely irrelevant because it's a routing operation. It's at L3. But my source network is relevant, right? Okay. I want to do a second question. Yeah, maybe I do it over there. Or maybe more the buddies over there. I don't know. Do I need to know my layer 2 VNI when I do VXLAN routing? Why? I have VNIX. So when my VLAN is not relevant in a routing operation, why is my VXLAN layer 2 VNI relevant? It's actually not, right? The reason why I'm asking this strange question is, how many VNI fields do I have in VXLAN NCAP? I have one, right? In a bridging operation, I use the layer 2 VNID. In a routing operation, I use the layer 3 VNID. The layer 2 VNID is mapped to my VLAN. The layer 3 VNID is mapped to my VRF. Does that make sense? Everyone okay with that? Yes? So let me go further. So we respawn now. My host 4 is sending traffic back to host 1. Obviously, it's again a routing operation, so we encapsulate again in VNIX. So we're using forth and back the same semantic of forwarding the traffic. Whenever it's routed, we use the VNID of the birth. Now, there could obviously be a situation where a host is unknown and routing should still work in that case. I mean, it would be bad if it would not, because it actually works in inter-VLAN routing today. So in this case, let's do host 1 to host 4 operation here. And we're going to my SVI, but my host 4 is not known. But as I have green, my SVI A, also on the same switch, I just route it in my destination network. And then I have a L2 stretch, the green stretch, as you can see, the layer 2 stretch. So I'm trying to reach my host 4 over that layer 2 stretch. So no traffic getting dropped, right? I just need to reach the destination subnet in a certain way. I don't care how. I just need to go into the destination network, the destination subnet, in the destination L2 stretch. Now when host 4 responds and hits SVIA, he actually responds based on the control plane. Why? Because host 1 is actually known in the control plane, because he started sending traffic, right? So we're using the VNIX for the return traffic. Any subsequent traffic will actually always use VNIX in that case, and we actually should be able to show that here. So when we go from green to red, we obviously know about that, so we reach from host 4, host 1 over VNIX. Everything is golden, nice, and beautiful. And then the response will actually go from host 1 over VNIX to host 4. So even with unknown hosts in routing operations, we can handle that efficiently, learn in band when we're actually forwarding traffic, updating the control plane, and subsequently have a more efficient forwarding happening in the network itself. Everyone, nobody able to follow, right? Yeah, no. It's tough stuff, right? But it's routing, right? It's routing. It's actually how MPLS works, basically, right? So let me show you a little bit things here, what we do in addition. So obviously there is an unknown host in a destination subnet. So how do I even know about that host? I mean, the /32 object is nowhere, right? That host never registered, so How can I reach a destination subnet which I don't even know about? It might be configured, but it might not be advertised to any network, to any control plane. So what we're actually doing there is we do an advertisement of an IP prefix route. EVPN allows that. We have different route types in there. One is a prefix route. And what we do basically is we redistribute the direct, which is nothing else than the subnet which is configured under the SVI, and the route map actually matches a certain tag there. And with this, we always find the destination. At least we find the destination subnet. So this gives me a little bit of a segue. Tomorrow morning, 8 o'clock, early morning, sorry about that, in a room right behind this one, we're going to talk about how to deploy VXLAN EVPN networks in a data center. So we're going a little bit deeper. We're talking about underlay and overlay designs, talking a little bit about control plane and configuration. That gets nerdy. Hope that's not too nerdy yet. So if you want to join me, that would be 8 o'clock. It's right after the run we do up the stairs and down, like on the other side of the building, without me. Let me do the packet walk now for between subnets. So this is actually the situation where VM1 and PM2 is in different subnets, right? Before we were the same, we did bridging there. Yeah, we were in the same subnet, but now we're actually separating that. So we have, as you can see, an SVI IP address for the subnet of VM1, which is 10.10.1, and we have a MAC address, which is 0002 dead beef. And then on the other side, we have an IP address for the gateway 2020-21, which is serving PM2, and we have the same gateway there. So we send obviously an ARP request to my gateway. I want to go to a remote network, so my DMAC, my destination MAC is actually my gateway MAC. We look it up, we learn, we update the control plane with all the information which is necessary for that local host for VM1, and then we actually get a response there, and we know now PM2 is somewhere remote, right? We know about that now. So we can forward now to the gateway MAC. So we send the packet to the gateway MAC, to my gateway, my first hop, and we do a routing lookup. Now, as my SVI sits in a VRF, I do the routing lookup in the respective VRF. And it gives me basically the IP address of 2020-2020 is behind the destination Tor loopback 0, which is the VTAP loopback there. And it is in the VRF VNI of 50,000. So all the traffic you're sending over there is going with my 50,000 VNI, which was my blue VNI, that VNIX we used before. So it's post-routing, right? So we encapsulate it, and you will see whenever you see post-routed traffic from one VTAP to the other one, we use the VRF VNI, and that's here 50,000 in that respective case. So we send it across, and now, when you look at the encapsulation respectively, and I know it should be okay, right? Yeah, it might be a little bit small. Source IP, destination IP is VTAP IP. Clear, good, right? That's outside. That's how we reach the different VTAPs. Now, when we look in the source MAC and destination MAC of that packet, we actually changed the source MAC to the MAC address of the first switch, because we did post-routing, right? We don't get the MAC again from the end host, which are actually from VM1. We lost that with routing, so we now only know, okay, my router MAC, basically, from the source. And my destination is also the router MAC. You remember when I said we had in the control plane not only the IP address of the VTAP, we also have the MAC address of the VTAP? That's the reason why. We don't have to look that up. We know about that. We know about L2 and L3 information of my VTAP, so I send it to the other side. And then obviously I have the source IP and destination IP of the original hosts, VM1 to PM2. So I forward that, encapsulate it across the network. I do a local lookup to figure out where do I have to send the packet to. After decapsulating, I send it down the classic Ethernet wire with a source MAC from the gateway, because it came from a routed operation, so the gateway is my original MAC there, and my destination MAC is then obviously PM2, which is the destination host I want to reach. So this is routing. And when you look at it, it is routing with a transit segment in between, nothing else. Everyone good so far? A lot of details, I know. We have 2 hours tomorrow morning to go to that again. And now to the question of the gentleman over there. With the distributed Anycast gateway, the MAC address and the IP address for that gateway, you remember we had that special command? We're not advertising this information into the layer 2 segment of VXLAN. That stays local to me. We only advertise that into the classic Ethernet segment. With this, there is no duplicate IP or duplicate MAC from a gateway perspective. And with the control plane we have behind of EVPN, we have all the MAC and IP reachability of the end hosts. So with this, I don't have to care on anything which could be duplicate in that case or which could cause an issue, because we already automatically filter it, and no, you don't have to configure anything in that regards. It's just a command to make the gateway an Anycast gateway. One thing you require is the control plane, so we can route and forward efficiently. But what you don't need at all is anything like HSRP or GLBP or VRP. There is nothing like first hop redundancy protocol running in between. So all these different switches are completely autonomous. They don't have to wait for a hello for another gateway to come up. They're all active. So what's my convergence then on the first hop? It's nothing, right? It's the ARP request from the end host. And as all the different gateways, all the different VTAPs for a given segment is using the same IP and MAC, do I have to re-ARP when I move? No, I don't have to. It's the same IP and the same MAC. At least when I stay in the same VLAN in there. All right, so let's look a little bit on another aspect there. So we did a lot of L3 and L2 forwarding right now. So let's look a little bit on the manageability and the configuration aspects in here. And I want to then take the opportunity to get another couple of questions going in here. So when we use networks these days, we configured every VLAN everywhere, right? That was consistently across my network, and that's what you see basically on the left-hand side. Whatever I configured, oh, new VLAN, go to every switch, do it. Could do that, but if there is no host connected, why should I? So with provisioning automation tools, we are trying to go more into a scoped configuration where we only configure what we really need to have on a given switch. If there's no host in VLAN 10 behind a given switch, why should I configure it? There's no reason for that. So save your resource there. And with the management tools we're using these days, and the management capabilities we use these days, we can do that in a very automated and efficient way there. So no more every VLAN everywhere. You can choose what you actually want, and even the VLAN has not even a significance anymore other than local. So let me explain this here, and when you look at this specific slide, you see on top something which is called vCloud Director. Let's call it an orchestrator, just a little bit more general. Could be anything, basically. On the other side, you have a network manager or network manager controller, or whatever you want to call it exactly. It's a tool which takes care on your network itself. And underneath, you have your switching environment. So what we try to do is abstract actually the individual switches in more a systematic approach to say, hey, whenever you need to do something to configure on a given switch, I'm network management tool, I know about that. You just tell me, dear orchestrator, what you actually need. And that's exactly what this is representing here. The orchestrator talks to the network manager or network controller. The network manager or network controller takes care on the configuration itself in the physical network. Now, when we're creating a virtual machine, for example, we're having there obviously the orchestrator or the VMM, which needs to create a virtual VLAN or virtual switch VLAN or something like that. So we need there a little bit help there, but the orchestrator puts that together. When the VM comes online, it could be a trigger from the bottom, or it could be a trigger from the top, which basically instructs the network management tool to create the configuration on top of these switches in that scoped way. Sounds fancy, right? That's cloud, I guess. I don't remember exactly. But let's go a little bit more in details. So I have new virtual machines coming online, and this is what we call a bottom-up trigger. So we have a new virtual machine coming online, and that virtual machine actually triggers on the switch with certain different protocols or different methods and gives them additional information. So as you can see there, we're using things like just a new MAC learn or LDP, or we use VM tracker integration, or maybe just a CLI. I want to execute the CLI. Could also be a trigger there. Or then even more fancy, there's the protocol which is called VDP, Virtual Station and Discovery Protocol, which is part of 802.1 QBG standard. So this is all potential trigger which are telling me there's something new happening down south of me at the switch. There's a new VM or a new physical machine coming online, and I tell you about that. I can give you more information like a VLAN tag, for example, or a segment ID. So with this, I go and query a repository. A configuration repository, you see an LDAP in there. And depending on which trigger I use, I have a different identifier and go and get this information out of that database and instantiate that down on the switch. And now with this, I have a location information because the switch went there and queried this information and downloaded it. So who entered the information in that LDAP database? It was basically the orchestrator. He told that network manager controller to store it. And that's behind that we have, for example, an LDAP database. That's a pretty efficient way of getting information down into switches in a very localized way. Now, we can turn that around and say, no bottom-up trigger. I'm telling where to configure, and there the VMM or the orchestrator has information about location of a hypervisor. Could, for example, know, hey, okay, that VM goes on hypervisor 1. Hypervisor 1 is connected to switch 1. Let's just do it there. And again, we're going back into a scoped configuration and not everything everywhere. So before I continue into multi-data center, Victor, Brian, are there any questions which should be answered verbally? Are we good? Let me come closer to you.
Whether you route within the same TOR or you go across multiple TORs.
Okay.
How many times is it TTL?
Okay. Okay. So the question is in regards to TTL decrements when we route. And thanks, Victor. I'm coming close to you to get you. So when we route on the same switch, we have a TTL of 1, which gets reduced, right? In, out. When we route across the segment, we're actually reducing the TTL by 2. We're routing into the first switch. It's first TTL which gets reducted. We're crossing the network, and then we do the end lookup, we decrement once again. Because we have an ingress hop and an egress hop. Great. All right, let's go into multi-data center connectivity, LAN extension, and IP mobility. And I guess everyone is asking already, let's do VXLAN for DCI. Yeehaw. Okay, let's see. What we actually want to have from a general perspective in data centers, yes, there could be the requirement for a LAN extension. Could be something like OTV. Could be something like EVPN, which allows me to stretch these information there. Any kind of Ethernet extension in there. But with this comes the question of where do I actually ingress my data center as I have now my network stretched across both. And that's where we see the Lisp approach being the predominant approach. You can still, if you want to, and feel free to do so, advertise /32 routes in your network WAN or in your provider's WAN if you want to. Probably he will call you 5 minutes later and are you guys crazy or what are you doing? So Lisp actually allows you to have no states in the underlay at all. You basically impose a network on top of. The same thing what we're doing in the data center itself at VXLAN. You do it in your WAN. and Lisp is taking care of all these different information. And as Lisp is not using a push approach for routing information like BGP does, it does a pull. I have no state in the underlay. I only have the state which I require, and when I talk about state, it's a route, for example, in order to follow the path to the right destination into the right data center from beginning. Now the top is actually addressing the, let's use VXLAN as a LAN extension, and when we're doing this, it is Tor to Tor. If I have on the left-hand side the data center and the right-hand side the data center, both data centers are VXLAN enabled, I use the EVPN control plane, I start encapsulating into VXLAN where my source host is as close as possible. I cross the whole network until the final destination where my destination host is. And now we have an end-to-end encapsulation, which is actually what we try to not do in regards to data center interconnect, specifically in the layer 2 area. We try to separate them, the data plane as well as the control plane. So when you look at the lower line with the green check mark, you actually see VXLAN, a handoff to another technology. And I'm going to show a little bit more about that in a second. But these are some of the concepts. I mean, we're doing data center interconnect for years, and I think we're presenting OTV and CiscoLive for 100 years plus or something like that. It's always nice to see that there are proven approaches in the industry which actually evolved a lot of thinking, and I mean the VXLAN as a LAN extension is obviously also which addresses, which goes into that direction as well. We want to have a separation in there, and let me show you a little bit more clear what I mean with this separation. So in the control, Victor.
So I don't know if this works. Does it work?
It works.
I was gonna say, it's only been 5 years, but to your point, it's been 5 dog years. So it does feel like 100 years, but it's only been 5 years. I just found the original slides just last week. But
Thanks, Victor. It's always fun. By the way, Brian is going to present OTV right after this. So if you have nothing, no beer or wine plans, which room is it, Brian? 6E? That's right around the corner. So you go out, get a coffee, get in the next room, and get the addition to this one here, and then. Okay. So let me go into the scoping of VXLAN and what we mean in there, that we want to have separate boundaries and what VXLAN can provide or not provide. In VXLAN with EVPN, we have that control plane, and we obviously can build a control plane domain within one data center and also a control plane domain in the other data center where we say that's iBGP. And then in between the data center, we use an external BGP kind of peering there. It's nice, it's cool, right? So my control plane is separated. Perfect. My WAN or my L3 domain down there doesn't even have a clue about the /32s or anything like that. We don't want to set that there, so we do right away data center 1 to data center 2 peering from the border leaves in that red line you're seeing down there, which is noted as eBGP. Now, eBGP has something which is called, whenever I go from iBGP into eBGP, I do next hop self. That does not work. Because actually my control plane tells them PM2 is behind that border leaf where green goes into red. Is that true? No, it's actually not true. It's a layer 3 segment in between, right? That does not work there. So when I want to do this, I have to change BGP to do next hop unchanged. That's what I have to do. And as a result of the next hop unchanged, let me go right away here. We're starting the end cap on that gateway on the very left-hand side. And where do we go? Where's my detour? My destination Tor is all on the other end. And where is now my data plane separation? Whatever goes into my VXLAN on the left top of rack on my source Tor ends up on the other side in the end. Please.
From EBGP perspective, there's no latency requirements. It's more data playing what your app can handle, right, in this situation?
From EBGP, there is no requirement, was the question in regards to latency. No, there is no. I mean, it is EBGP. It's what we use for years. So it's, I mean, we did very fancy stuff in regards to distance there. So it's nothing.
For server A, server B, how much can it handle in terms of how far it can be in this situation, right?
The question is, it's in regards what can server A, server B handle. It's actually not the server itself. It is the top of rack where the VTAP is terminated. In this specific example here, and I think I had once a hidden slide which is showing that, my source VTAP needs to store all the potential destination VTAPs which exist in the network, which are serving that same VNI. And obviously a table is a finite table when I program it in hardware. So let's think of that poor little switch which you bought in Costco for $50, and he has to store 1,000 remote VTAPs. He is probably, it will blow his mind, like my blind mind is sometimes blown when I look at that stuff here. So yes, so this is just one of the scale implications you might have in there to spin that a little bit more. But generally, to come back, everything I send into the source switch where my host is connected ends up on the destination. When we look at OTV, what we did over time, we can separate things. And when we separate things, different opportunities come in. Let me give you another example. If I have 10 TORs, each TOR receives 1% bump traffic. And I have storm control at 10% on each individual port. That makes still 10% on my DCI of bump traffic which goes through, for example, broadcast, right? I maybe don't want half that. Now, when I go in a different approach where I can separate the end cap, like shown here, I can take the cumulated broadcast traffic as an example on the border between the core and the CRS1 there. I have a better view. These are two separate fabrics, yes. There's two separate fabrics to come to your question. So let me go back here just to complete the whole thought process and also give that specific slide here a little bit to show. You see here P1 MAC, PM1 MAC, PM2 MAC. You see source TOR, destination TOR. So this is what I get from BGP, right? So it really starts happening end to end with the next hop on change, and that's where the encapsulation goes exactly as shown here this way. Now, we have a way in order to separate that, and that way is called normalization. It's a very fancy word, but I think we all used these terminology of normalization is nothing else than between CRS1 and core. What is there? What's the most common normalization layer in layer 2? It's called Ethernet and .1Q. So you separate your traffic coming from the access on the core where we exit in direction of the CRS. So you stop there, classic Ethernet, you cross it to CRS1, and you impose at CRS1 an overlay technology, which is capable to do L2, L3 transport. You end on the other side on the CRS1, go into an Ethernet normalization, and then go into the other completely separated VXLAN domain in data center 2. And with this, I can also have independent addressing schemes from an L2 perspective, different L2 VNIs, different L3 VNIs, because I normalize on an Ethernet layer in between. Actually, that's the much better picture for that. We have our VXLAN domain down south. We have the boundary. At the boundary where we see that VPC, we have a VPC domain there. We redundantly connect into OTV. One OTV edge device, the other OTV edge device. We have the joint interfaces fading into the IP MPLS core. I extend that with layer 2 to the other side. And again, my domain is completely separated. And I can start doing all these functions like storm control or additional filter on that leg between the VXLAN L2 gateway and the OTV VDC or the OTV device. Excuse me? Can I collapse the middle and the top? I can collapse it on the same switch with two VDCs, yes. I cannot collapse it into the same VDC. So I need to still have VDC separation for VXLAN and OTV. Yes, please.
Is there any roadmap on the VXLAN optimization in order to fully replace OTV?
I love these questions. What we're currently doing is we're adding VXLAN as an encapsulation to OTV. OTV is more than just encapsulation and a control plane protocol. There are a lot of hooks in there which help me to actually make it a proper DCI technology, and that's our leading solution today, but we enhance it with VXLAN from that perspective. We're working on solutions to get VXLAN becoming a DCI. There are a couple of things which need to be done in the control plane. Functionality, meaning different little things which are missing today. We're talking about encapsulation, data plane separation. Yes, we're working on this, but this is not a committed roadmap or something like that. We have to evolve the industry standards to get there. Good, Victor? Good. So normally, if Victor would have a voice, he would be up here with me and take the residing 20 minutes to talk about. Oh no, he's doing it. No, that's good. That's good.
Well, so your question, is there a roadmap? Yes. Now, to Luca's point that we're adding VXLAN encapsulation to OTV, I have the napkin at home. VXLAN was never VXLAN, it was OTV first. It was the OTV encapsulation. If you look at the UDP port number that was assigned to VXLAN originally, it actually Dino filed for it as an individual rather than for Cisco. But it was the OTV UDP encap. So without getting into too much history, the 5 years of OTV have been dog years in maturing a technology that is not trivial when you want to multi-home layer 2 networks. And when you want to also quench and limit the scope of layer 2 failures, right? So we know how to do this. It's actually written on paper in all the RFCs and drafts for EVPN. Implementing that is a different story, and we're going to do it. It's going to take some time. So while things mature, there's technology that's shipping and proven, tested, scaled. So yes, but be patient, right? Don't get ahead of yourselves. There's some areas where this is ready for prime time. There's other areas where do your analysis carefully because the combination may render better results in the short term. Eventually, we want one thing, okay?
With great power, great responsibility, right? I mean, not yet at Star Wars, so, but goes into that direction. Okay, let me go into the mobility space a little bit with multi-data center, and I think we have 15 minutes left, right? So it's getting tough, but the good thing is the whole last section we're having actually in that slide deck, you're going to see a lot more and more details tomorrow, 8 o'clock. So yeah, we have to go and do the run, the stairs up and down. I should do that. Okay, so in the VXLAN data center itself, we're having the host routes. The host routes are getting distributed in the control plane respectively. And at the border, where we have the N7Ks or the ASRs, we are actually start doing a direct mapping into the Lisp system. So with this, we have all the information, right? We know everything. Coming from a Lisp side up north, from a Lisp-enabled host or Lisp-enabled endpoint, going into the data center, and in the right data center where actually the respective host resides. And then from the border, we're actually going into it in the VXLAN case. And when we're moving, when we're moving to the other side, we're obviously updating the Lisp signaling and make sure that subsequent traffic hits the right data center afterwards. So this is our integrated handoff. And the Nexus 7000 with its 7.2 release, which is actually, that's recorded, right? Okay, let's say maybe tomorrow or the day after, will find its light, has an integrated VXLAN EVPN to Lisp gateway functionality. So it's not even that you need to have 1 box, 2 box, 3 box, 4 box to put something together. You can do that in 1 box, VXLAN EVPN to the NAND 7K with the F3 line cards, and then hand it off into your WAN space to optimize the ingress routing, as well as have an option to do the VPN tenant mapping more efficiently in the network itself. Okay, let's look a little bit at the details here. So we have back there a host. I guess that's the one down here behind CiscoLive. And that host is behind a given endpoint that gets signalized up north. And when we look at the Lisp mapping system, we see actually that host is in data center 1 at that given time. So with this, we're sending all the traffic into data center 1 with the Lisp encapsulation, decapsulate, and send it down with VXLAN to the end host. If that host moves, and yeah, it was the host down behind CiscoLive, we obviously have a move event, and we're signalizing this move event to my VXLAN EVPN control plane. And with this update, I will also notify this information and send it into the Lisp map system. So I have an update, right? Now, that host is not anymore in DC2, in DC1, it's in DC2 now. So please send that traffic to DC2. So we actually subsequently, was there something happened? Yeah, here it is. Here's the DC2 in red now. We actually do have an alternative path now to send the traffic down, but it's not yet active, right? So we're basically sending the information also down to the tunnel edge router, which is responsible for the data center 1. And then with this, we're actually actively activating the new path. Where is it? Where is it? Oh, sorry. To the red side, to the data center 2. It's just signalization, right? And the flow gets seamlessly diverted to the other data center. And it's an integrated approach, as previously said, with the Nexus 7000 doing both there. And sorry for the marketing here. So let's go a little bit into the underlay deployment consideration, because you have to build a network underneath for VXLAN. And again, it's for all the CCIEs. For the multicast-enabled underlays, we obviously have PIM, which is the protocol-independent multicast routing protocol in there. But when I integrate software VTAPs, I don't have to care that much on this because we're using IGMP at that space. So it's much easier for the software VTAPs or the host overlay components. The hardware VTAPs will talk PIM and are actively participating in that multicast routed network underneath there. Now, there's a little bit of a crux with these protocols there. So it's a hardware dependency which is around. So different platforms today have a different state of PIM capabilities for VTAP traffic. So that's basically represented in here. You see there, Nexus 7000 is pretty flexible, can do PIM ASM BIDIR. We have a Nexus 5K where we actually focus on BIDIR only in that regard to Nexus 9K, which is doing ASM and BIDIR going forward. So it looks like that we are aligning all together towards summer end of the year into a PIM BIDIR state to have most efficient multicast happening in there. Multipathing entropy. Initially, I said that we have that source port, which is ever changing. So we get a classic Ethernet frame in. We look at the different tuples we have. We build a hash accordingly, put it into the source port of the encapsulation. And with this, we can distribute the traffic more efficiently across a routed network, have less information which are the same, meaning that source port which is ever changing based on the traffic flow in there. Topologies itself, I mean, this is what we call a folded cloth. And it has our spine leaf, if you want so, where we have the L2, L3 gateways on the bottom, my leaf layer. And we have a lean spine on the top, which is actually nothing else than an L3 forwarder. All the VTAPs, all the intelligence is actually happening at the leaf. At the border leaf, that's where we do the encapsulation and the decapsulation, and the spine is there to efficiently forward east-west traffic in that case. Access aggregation, core or wide bandwidth topology if you want. So we have the access, which is again the L2, L3 boundary there. We have an aggregation layer in the middle, which just helps us to distribute the ports. And then on top, we have a core, which is basically the L2, L3 handoff into another technology at that case. The gateway we obviously want to have, the gateway is what we want to handle at the access layer also in that respective scenario here. Now, why do we want to have actually the gateway always being on the TOR? There are a couple of things which ease this deployment when we have it, when we have the gateways at the access instead of at the core or at the distribution. One example is here. When I use HSRP with VPC together, I can have 2 guys being active. When I have 4 spines, what am I doing with the other 2s? That's basically the left example, which I have to distribute odd and even VNIs, for example, or separate the exit point for a first hop routing in that case. When I do the first hop routing already at the access layer and only introduce at the core layer a routed gateway, meaning only routing, I can use ECMP because I don't have to rely on any synchronization or first hop redundancy protocol in order to get that going. I just do my first hop routing, go into the VXLAN L3 service, reach the core on the top as represented in that slide, and then leave it routed. So no VPC, no HSRP or anything like that being in the case there. So you can really use all the bandwidth and all the boxes regardingly to forward the traffic there. In regards to instrumentation or visibility, I mean, we're encapsulating, right? So I have no clue what you're actually doing because it's IP-UDP traffic, so what it is. So we're actually having capabilities in the hardware as well as in the software to have a little bit more information than just its IP-UDP traffic, and specifically with the network analysis module, the NAM, we can decapsulate traffic in flight on the Nexus 7000. Regardless of this, there is efforts we are doing in regards to OAM, operations and management, in there for VXLAN, and we're driving the standards in there to have a trace route, you're executing it over your overlay, actually mapping to your underlay information and give you more granularity. I think this is one of the most elementary pieces we have, which the industry needs to deliver in regards to VXLAN management, and we're actually pretty leapfrogging that piece there and having a lot of solutions coming up in that regards. Overspeed, I mean the encapsulation, it is a couple of bytes which are on top of it, 50 or 54, which results that obviously the speed you're ingressing with 10 gig is a little bit more than 10 gig when you egress the switch in an encapsulated way. So think of this piece there, and so with the overspeed of from getting in from 10 gig into 40 gig, you accommodate that easily and nicely. So I think that's, are we in time? I think we're pretty good in time. So let's look at the summary and conclusion now. There are a couple of things I just want to recap here. So the optimization of the L2 and the L3 gateway in VXLAN, it's pretty significant what we did there, and I think the top of rack with the distributed Anycast gateway really knocks it out there. Layer 2, Layer 3 services, multi-tenancy, the EVPN control plane helps seamlessly there, and VXLAN as an encapsulation is obviously very nicely being available there and providing this service to you. Always keep track on when you design your underlay, which is your routed fabric, in order to get VXLAN running on top of it, how you do that, how you work in that direction. When you go DCI, think about push and pull. Push the routing protocols versus pull Lisp being in there with a MapDB approach. Think about the integrated gateways we are providing, and also the L3 gateway at the border, which simplifies basically your forwarding outside the VXLAN network itself. So with this, participate in my favorite speaker. It was Victor. I'm just his voice today, so. There is no Twitter handle there, so if you want to participate. But with this, thanks very much. Thanks for the time, the 2 hours. If there are no questions, I let you guys go a little bit early. Thanks a lot, and bye-bye.